So we'll start with the problem. We're going to find the surface for all the points which satisfy the following. The gradient at x, y, z is perpendicular to the gradient at 0, 0, 0. In other words, the gradient at the origin. And our function, well, it's not just any function. This function right here. Well, Now, when you see the words is perpendicular, that's code. So how do we know if two things are perpendicular? Well, that says that they're perpendicular if their dot product is 0. Now you might say, wait a second, how do we know that these are vectors? Well, because we're talking about the gradient. And the gradient is a vector. So that says, okay, we really need to know when is this true. So what does that say? Well, let's find the gradient. Let's find that at 0, 0, 0. Let's take the dot product, simplify, and we'll see what we get. So, what's the gradient? The gradient of g, x, y, z is, well, look for all the x's. There's an x here. So that's e to the x minus 2z. There's an x. Derivative of x times y. With respect to x is y. And there's another x. So there's 1. And that's it for the x's, comma. See, now we're doing with respect to y. There's a y there. So cosine of y plus 3z. And there's a y. So plus x. And there's another y. So plus 4z and minus 4. All right. Now with respect to z, so minus 2 e to the x minus 2z. And, there's another z. Chain rule. So plus, that'll be 3 cosine y plus 3z. And there's a z there. Plus 4y. And that's it for z. Done. Okay, so there's our gradient of g. Now, what's our gradient of g at 0, 0, 0? Well, the good news is 0, 0, 0 is easy to evaluate. So we're going to get e to the 0 plus 0 plus 1. All right, well, that'll be simple. Then we're going to get cosine of 0 plus 0 plus 0 minus 4. Then we're going to get minus 2 e to the 0 plus 3 cosine of 0 plus 0. Well, let's see, what does that become? 1 plus 0 plus 1 is 2. 1 plus 0 minus 4, negative 3, minus 2 plus 3 plus 0. So that's 1. Minus 2, 2, comma, minus 3, comma, 1. All right. Well, so that's what we're going to take the dot product. So remember, we're going to dot original gradient with this 0, 0, 0, and we're going to see what we get. And the answer is we're going to get a really big expression. So this is not a hard problem yet. Hopefully it doesn't become one. But we just have to be patient. Make sure we don't rush. We copy everything down correctly. And then life is okay. So first we're writing down our gradient. And now, once our gradient is done, we're going to dot it with 2, negative 3, 1. Which means we're going to get 2 times what's in the first entry minus 3 times what's in the second entry and then we're going to have plus 1 times what's in our last entry. And once we take a look at this, all this is going to be equal to 0. Well, let's see if it doesn't simplify. Now, reasonably speaking, it shouldn't simplify. However, in mathematics, oftentimes unreasonable things happen, and this isn't just some random function, it was well chosen. Notice that we have 2 e to the x minus 2z. Over here we have minus 2 times e to the x minus 2z, and therefore those things will cancel. Here we have minus 3 times cosine of y plus 3z. Here we have plus 3 times cosine of y plus 3z. So those will actually cancel as well. So what we end up with is actually something a lot easier to think about. So 2y plus 2 minus 3x, and then minus 12z and plus 12. All right, it's not so bad. That's not so bad at all. And then anything else? Oh yeah, there's a plus 4y here on the end. So we have negative 3x, 2y plus 4y makes 6y, and minus 12z. Then we have 12 plus 2, which is 14, and that equals 0. And you say, okay, that's something we recognize. In fact, if we remove these to the other side, we would end up with 3x minus 6y plus 12z equals 14. So it turns out that all the points where the gradient is perpendicular to what the gradient is at the origin turns out to form a nice plane. Ah, that's interesting. Of course, we wouldn't expect that in general, but hey, it's fun when it happens. All right. So, what are we talking about? Well, last time we talked about the gradient. The gradient is really nice and important. In fact, you get a lot of information out of the gradient. Now, how do we think of the gradient? Well, there's a couple of things that we can think about. One is we can really say, hey, you know, the gradient is acting a lot like our derivative. And so we saw a few things, and let's write down a couple of facts that we know. We know that when we talk about the tangent planes, you can write as z minus f of ab is equal to partial f partial x at ab times x minus a plus partial f partial y at ab times y minus b. But that can be rewritten as, and this is what we saw last time, as if you grab those two partials derivatives, put them into one vector, partial f partial y, partial f partial x at ab, partial f partial y at ab, and dot it with x minus a, y minus b. So somehow this is acting in the role of what f prime of a was when we were talking about single variable calculus, and this was acting in the role of what x minus a was. So what was going on? Well, here this is looking at how much have you changed in your entries, your inputs. This is saying what's the rate of change based on what's happening to the inputs. And so if you put those two together, how much have you changed in the inputs together with the rate of change with respect to that input, what you'll find is the change. All right, well, that's not so unreasonable. So what do we do? Well, this now has a name. Multivariables, we call it the gradient. Gradient at a point AB. All right. So what else did we know? Well, there was one other thing that we saw. That we could use this gradient to do directional derivatives. So what is that? Well, you can imagine that you might be, say, standing on a hill somewhere. So here we are, standing, and we're thinking about math. Okay, so we should have a smile on our face. All right, this is probably not the best stick figure, but all right. So we're on a hill. Let's draw ourselves a hill. And now we might ask ourselves the question, all right, suppose that we move. So we head in a certain direction. And the question is, are we going uphill or are we going downhill? So you can imagine I say, well, I want to head, say, 60 degrees north-northwest, which is just a fancy way of saying I want to head in a particular direction. So what we can do is we can figure out the answer, are we going uphill or are we going downhill, by doing what's called a directional derivative. It's the rate of change in a particular direction. So what you do is you take the gradient of f dot u. So this tells us the rate of change in two particular directions, and when we dot it with u, where u is the unit vector of the direction we want to go, that helps us find the amount of change in our direction. Now, dot products, we studied those, and we remember a couple of facts. The big one is that v dot u is the magnitude of v times the magnitude of u times the cosine theta, where theta is the angle between u and v. Well, so we can apply it to this directional derivative. And if we do that, we say, okay, we get the following. That the directional derivative is, again, the gradient of f at p dot u. Well, that becomes the magnitude of the gradient of f of p times cosine theta. Now you might say, whoa, wait a second. What happened to u? Well, u is a unit vector. Length of a unit vector is 1. And therefore, it disappeared. All right. Well, how does that help us? We know something about cosine theta. Cosine theta is a nice function. So cosine theta is always between -1 and +1. And so, because we know this behavior, we can now say that the directional derivative is bounded. So the largest that the directional derivative can ever get at any particular point is the size of your gradient. The magnitude of the gradient is the maximum rate of change. And negative the magnitude of the gradient is the maximum amount of change in decreasing. So maximum decrease. So, now we know how to find maximum increase and maximum decrease. Well, where do we look? Suppose I want to achieve maximum increase. So, how do I do that? Well, I would need the cosine theta to be 1. Well, that means that theta is 0. If theta is 0 between two vectors, it means they point in the same direction. So, our first property of our gradient is that the gradient of f points in the direction of greatest increase. So if I want to answer the question, which way should I go to go up as fast as possible at a particular point? The answer is, always follow the gradient. The gradient knows the way. So, okay, so that's useful to know. Well, what's the rate of greatest increase? That's the answer is the magnitude. Suppose I don't want to go up. Suppose I want to go down. That's possible. And if I do want to go down, how do I do it? Well, cosine theta should be -1. And the angle for theta that does that is pi. And if two vectors have an angle of pi, that means that they're pointed exactly opposite. So that says I shouldn't be heading in the direction of the gradient. I should head negative the gradient. So negative the gradient points in the direction of greatest decrease. And of course, the rate of greatest decrease is negative the magnitude of the gradient. All right, so now we have all these useful information. Let's do an example. Let's find the unit vector pointing in the direction of the greatest decrease and the amount of greatest decrease at the point something. Well, we're going to go with 0, 0. Simple to work with. For the function, well, e to the 2x minus 4y plus 5y minus sine of 3x and plus 17. All right, there we go. So what do we do? Well, we start by saying, all right, whenever we see something that says greatest increase, greatest decrease, it's like we're trying to minimize or maximize the directional derivative. We say that's a property of the gradient. So the first thing we should do is we should find the gradient. So the gradient of f is, take the derivative with respect to x, 2 e to the 2x minus 4y. There's no x in there. Then minus 3 cosine 3x, and the derivative of 17, 0. Take the derivative with respect to y. Well, there's a y here, so we get minus 4 e to the 2x minus 4y, and then the root of a 5y is a plus 5, and there's no more y's, so that's it. Now that's the gradient of f at any particular point, but remember we're at the point 0, 0. So we really need to be at a specific point. So we plug in 0, 0. So we're going to get 2e to the 0 minus 3 cosine of 0, comma, negative 4 e to the 0 plus 5, and that becomes minus 1 plus 1. All right, good. Now, is that our answer? And why not? Well, it's not our answer. For one thing, this is the gradient. That's not pointing in the direction of decrease. Gradient points in the direction of increase. So we need to do something that flips it. So we say, okay, negate it. Negative the gradient of 0, 0. So that would be 1, negative 1. So this here, that points in direction of greatest decrease. Now, is this our answer? And why not? The answer is no, because it's not a unit vector. Okay, so we need to make it a unit vector. So let's take that. So 1, negative 1. Well, that turns out that's easy to find the magnitude of that vector. Square root of 2. So our direction of greatest decrease is the following. Namely, we take 1 over the square root of 2 times 1 minus 1. Now remember, there's a second part, the amount of greatest decrease. We'll say the rate of greatest decrease. We'll have that be our amount. What is that? Well, for that, we say, hey, it's the magnitude of it, which we actually computed here, and then it's a minus root 2. Now, before we go on, I should point something out. This actually is a nice idea, because you might be saying, okay, suppose I want to find a minimum value for a function. How do you go about finding a minimum? So there's something called gradient descent. And the idea of gradient descent says, hey, if I want to go to a smaller value, the idea is follow the gradient to get a smaller value. Because the gradient points in a direction, not just any direction, it goes, how do you go downhill as fast as possible? So if I want to get to a smaller value, follow the gradient to get smaller. And of course, we just keep following it, and eventually, where will it settle? Well, it'll settle into something which should be as small as possible. Now, of course, there's more challenges than just that, but this is a nice tool that gets used in mathematics. And the idea is basically saying, hey, because I know where things point, I can get information. And so that says that our gradient is a really nice and useful tool. And so we've already have some really amazing properties. And we're like, wow, this is fantastic. Can we really hope for anything more? And well, it turns out that yes, in fact, we can get something even more. Not just these properties here of the gradient, but if we act now, then we can get one more thing. And to get that special limited time offer, we have to go back and remember something about level curves. So let's recall what a level curve is. So suppose I have this surface here. So it's not flat, it's somewhat bent. And we say, okay, here's our surface. So I have this surface z equals f of x, y. That's my purple surface here. Then in the meantime, I also have this plane. So here's the plane z equals k. And what's happening is that the plane is coming through and slicing the surface. And when it slices, it'll intersect in these two curves. Now these two curves here translate in these two lines if we look from above. So what this is the plane z equals k from directly above. And so we're just seeing just sort of a little teeny tiny piece of the curve. Sorry, this curve, just a little tiny piece of our function that we're seeing. All right, so that's the level curve. Now that's not a new idea. But now let's ask a couple of questions and see what we can say. Suppose I'm on a level curve. So I'm on this level curve, and I move along the level curve. What's true? What's happening to my output? The answer is, I'm staying level. See, level curves, the idea of level curve is you always stay on the same level. I'm not moving up and I'm not moving down. So here, I'm staying on the level. Wait a second, if I'm not changing, what's true about z? And the answer is, it's not changing. So any derivative would be 0. So what's that right derivative to think about? So the answer is, suppose I'm now moving on this level curve. What direction am I moving? And what direction I'm moving is I'm moving in the direction of the tangent to the level curve. So what we have is, because we're constant on the level curve, the directional derivative of the function when we move tangent to the level curve, which basically says staying on the level curve. So as we stay on the level curve, the directional derivative should be 0. Okay, so that makes sense. We're not changing, the derivative should be 0. But now we go back a little bit and say, hold on, we know that directional derivative comes from a dot product. Dot product equaling 0, we talked about that in the example. We said, hey, dot product equals 0 means things are perpendicular. So our last nice fact is that the gradient is always perpendicular to every level curve. So if I find this level curve here, and I want to say, where's the gradient at? Well, we can actually say a little bit about where our gradient is. Now, one thing is, we know it's perpendicular. So we know it's got to be pointing in a perpendicular direction. But you might say, hold on, that's still not quite enough, because couldn't I be going perpendicular this way or perpendicular that way? The answer is, well, yeah, you could, but remember, how does the gradient point? The gradient points in direction of greatest increase. And if you look, if I want to go up, I've got to be moving towards the corners. I've got to move towards these backwards corners, which means that my gradient has to point in that way. That's the direction the gradient will point at that point. Now, you don't know, one thing is we don't know how long the gradient is, but at the very least we do know for sure it points in that way because it's pointing uphill. Well, how do we else do we use this? I mean, so we know how to find things which are perpendicular to level curves, but we can also say the same idea works for any higher dimensional setting. So I can go up and say, what about functions of 3 variables? So w is a g of x, y, and z. In that case, what's true is I can say that the level surface, so a level surface is g of x, y, z equals k. So for level surface, I'm going to have that my gradient is perpendicular to my level surface. Now, why is this so good? Well, perpendicular vectors, we like to think of these as our normal vectors. So that's telling us that gradients help find normal vectors, which means, really, that gradients can help find tangent planes. So remember, we talked about tangent planes already. So the first way we talked about tangent planes is we had these partial derivatives. We said, okay, so z I can think of as my function at my point plus how much do I change with respect to x times the amount of change in x, how much do I change with respect to y, times the amount of change in y. Now we say, well, what if we have a different kind of function? Not z equals f of xy, but maybe f of xyz equals k. We saw this type of thing when we did implicit differentiation. So we can think of this as either an implicit surface or as a level surface of some higher dimensional object which we don't have. And if that's the case, what we do is we use the gradient. So f of xyz equals k, we say, all right, the gradient vector at the point ABC, that's going to be perpendicular to the surface. And to be perpendicular to the surface means that when you zoom in, so you do your zoom action, the surface looks flat. And so when it looks flat, I mean, the surface looks like a plane. And so the normal vector, that's the normal vector is the gradient. So the gradient dot x minus a, y minus b, z minus c. In some sense, this makes sense. Okay, so the gradient is talking about our changes with respect to x, with respect to y, with respect to z. This is the amount of change, and it's as it all works out. Now you have two different methods. The question is, are they the same? And the answer is that when they are both applicable, they will give the same value. So if you compare, say, the method 2 versus method 1, I can start with z equals f of xy, and I can move the z across. So I can create a new function which has three variables, x, y, and z. That's f of xy minus z. Now I take the gradient. It would be f sub x, f sub y minus 1. And the point, well, a, b, f of a, b. So we get that our gradient, that's f sub x at ab, f sub y at ab, negative 1, x minus a, y minus b, z minus f of ab. Take the dot product, set it equal to 0. Then if you rearrange, and you're patient, very patient, not too bad, it turns out you get what you should get. So the two methods agree. Now, which one do you use? And the answer is you should know both. You definitely need to know method 2 because there are some things where method 1 just can't work. So it's a more universal method. But you know both. Know both. All right. So let's do an example. Find the tangent plane at the point 0, 1, 2 to the surface x squared plus e to the xz plus yz equals 2 plus cosine of xy. Now, it doesn't ask us to do this, but one thing we should sort of do as a sanity check is ask the question, is the point 0, 1, 2 on this surface? So let's just check that really quick. So let's see. Everywhere you see an x, put 0, so that would be 0 squared, e to the 0. That's good. Y times z, well, that would be 1 times 2, which is 2. Does this equal, question, 2 plus cosine of 0? Well, it turns out e to the 0 is 1, and cosine of 0 is 1. So 1 plus 2 does equal 2 plus 1. So yes. So 0, 1, 2 is on this surface. All right, so good. Now we say, all right, can we solve for z? And the answer is no, we can't. Because there's a z there, and there's a z there. In fact, we can't solve for any variable. That is to say, we can't solve for x as a function of y and z, can't solve for y as a function of x and z, and so forth and so on. So what can we do? Well, that says we really need to dig down and use method 2. So method 2, remember, what is that? F of x, y, z equals k. Now k can be any number, but it has to be a constant. Can we apply method 2? The answer is not yet. Well, what's wrong? Well, what's wrong is there's functions on both sides. Both sides are changing. We really need to have one side be a constant. But that's almost always super easy to fix. Because you can just say, hey, let me move stuff across. Now, definitely move the cosine of xy across. The 2, it doesn't matter if you move it or not. So if you move the xy across, then we'll get x squared, the cosine of xy, plus e to the xz plus yz minus cosine of xy equals 2. So there's our f of x, y, z, this whole expression. All right, well, so next thing is take the gradient. So the gradient of f is, so go through, take derivative with respect to x. There's a 2x, and then there's a z, e to the xz. No x there. There is an x there. Derivative of cosine, by the way, is negative sign, so this will become a plus y sine of xy, comma. Now take derivative with respect to y. There's no y, there's no y. There's a y. So that would be z. There's a y there as well. So plus x sine of xy, comma. Now we look for the z's. There's a z up here. So that'll be x, e to the xz. And, oh, there's a z as well, plus y. And that's it. That's it. All right, so we've had our gradient. Now, the next thing is we have to take our gradient at a point. See, the gradient is not a normal vector until you evaluate it at a point. It's the evaluation of a point that turns it into a normal vector. Because normal vectors should not vary with x, y, and z. Normal vectors should be vectors. All right, so we're going to plug in 0, 1, and 2. Which means everywhere we see x, it becomes 0. That's going to make it really easy. So let's see. 2 times 0, 0, gone. Then we're going to have 2 times e to the 0. So that's going to be 2 plus 1 times sine of 0. Well, sine of 0 is 0. So that's gone, comma. And then we have z, which is 2 plus 0 times sine of 0. Well, that's extra 0e. So yeah, that's definitely gone. So that's 2. Again, 0 e to the 0, that's 0, plus y. 1. 2, 2, 1. Now, that's our gradient. Now at this point, if we wanted to do the tangent plane, there are sort of two options. Our old mindset said, hey, those are the coefficients. So we get 2x plus 2y plus z equals something. How do you find the something? Well, you plug in the point 0, 1, 2. So when you plug in 0, 1, 2, 0 plus 2 plus 2 gives 4. And that is a correct answer. Well, that's not the only thing we could do. We could do other things. So what are some other things we could do? Well, we could say the following. Remember, what do you have? The gradient of f at a, b, c dotted with x minus a, y minus b, z minus c is equal to 0. So for us, we could say 2, 2, 1 dotted with, now x minus, here is our a, b, c. So x minus 0, y minus 1, z minus 2 equals 0. Or 2 times x minus 0 plus 2 times y minus 1 plus z minus 2 equals 0. And that's the other way we could write it. Now, which way is best? And the answer is it depends what you're doing. It really does. And so be open to different possibilities. Now, the reason you may want to have it in this form, we'll see some examples later on, is when we're really trying to say, let's focus on differences. Because this expression really says what are our changes, our differences. So if you're after differences, that is the preferred form to use. All right, well, let's see another example. So let's find the tangent plane to something. Well, what could we choose? All right, well, let's choose the following. 12 x cubed plus 9yz plus log of xz equals 3. Now, we're not done yet, because the question is, that's not just a surface, we need a point. At the point 1, negative 1, 1. Now, where does that point come from? Well, it's just a point. Now, the question is that actually a point on the surface? Well, you can check. So here, you'd have 12 times 1, then plus 9 times negative 1, so that would be 12 minus 9. Then here it would be plus log of 1, which is 0. 12 minus 9 plus 0 does in fact equal 3. So it is a point on the surface. And now it's in really good form. Easy for us to work with. This is our capital F of x, y, z. And so we can say, find the gradient of f. And what would that be? Well, 36x squared. There's no x in the second term. And in the last term, well, it's 1 over xz times z, which simplifies to 1 over x. So second term is with respect to y. There's no y. Here, there's a 9z. And the last term, well, you're going to get no y, so that goes away. Finally, with respect to z, there's no z. Here you get 9y. And we take this with respect to z, you get 1 over xz times x, which simplifies to 1 over z. Now, on a side note, we could have said, hey, log of xz. You could have said that's log of x plus log of z. And then you're like, ah, okay, so yeah, 1 over x, 1 over z. So that's not so surprising. Evaluate. So gradient of f at 1, negative 1, 1. So where we see an x, we put a 1. So we get 36 plus 1, which is 37. Here, where we see a z, we put a 1. So that would be plus 9. Where we see a y, we put minus 1. So this would be minus 9 plus 1, which makes this, of course, negative 8. So we end up with 37x plus 9y minus 8z equals something. Well, what? Plug in 1, negative 1, 1. You get 37 minus 9 minus 8. Well, that's minus 17. 37 minus 17 is 20. So that's what goes here. And we're done. Okay. So finding tangent planes to surfaces is actually a very straightforward process now. Move everything to one side, take the gradient, evaluate the gradient, there's your normal, and now set up your plane. So it's a very quick process. So once you remember the process, well, you're good to go. All right. So now on to the other topic for today, which is about estimation. And this is a really important idea in calculus, is linear estimation. Now, when you see the word linear, you should think of this as saying flat. And for us, when we think of the word flat, we're really thinking of things like tangent. In Calc 1, where we did one-dimensional, that was tangent line. And in Calc 3, we're in three-dimensional, or higher in some cases, that means tangent planes. So we can use tangent planes to approximate the values of the function. Which, what does that really get to? Well, it says, if you have your three-dimensional space, and you say, all right, sitting in my three-dimensional space, I have this function doing all sorts of weird, wacky stuff, and I want to say, well, what's happening here? Well, if you were to take this and to zoom in, what you would see is that close by, it's behaving like a very flat thing. So much so that if you look at the difference between the function versus the tangent plane, it's almost imperceptible. You can barely tell the difference. So that the tangent plane is a good approximator. That's what we have. The tangent plane is a good approximator close by. So, what do we get? Well, rearranging, we can say that the difference in the output, f of AB versus f of xy, we call that the change in z. That's f sub x at AB times the change in x, plus f sub y at AB times the change in y. So this is a way of saying our tangent plane is a good estimate for our function nearby. So, by the way, in case you're wondering where does AB fit in the picture, AB is in your xy plane. It's where you're evaluating your function by at. And so what it says here is if I'm nearby, my surface is being well approximated by my tangent plane. So, all right, good. Now, sometimes you'll see something called differential notation. The idea of differential notation says, instead of doing an approximation, we're going to do an exact thing. And so we use the d instead of the delta. It's a convention. Don't worry too much about it. It never really comes into play in any excessive amount. It basically says, look, if you're on the tangent plane, then you're smooth. And linear estimates are linear exactness. So life is good. All right, so how do we do this? Well, suppose we're given that f of xy is 2x cubed plus xy minus y cubed. And we want to approximate what is f of 2.03 comma 0.98. Now, you might say, well, let's just plug it into a calculator. But of course, we are in our hypothetical desert island, and we don't have a calculator anymore. So, okay, why do we want to compute this value? Well, we need something to pass the time. So we say, all right, well, what's the key? Well, the key is we see this word approximate. So if you see any word like that, approximate or estimate, what that means is we don't need to do the exact thing. What it means is use the tangent plane to say what should happen nearby. What should happen nearby? So we look at this and say, okay, 2.03, 0.98. Well, that's close to a set of numbers which is really easy to work with. And so we can say, one way we could do this is to say this is what's the function at 2, 1. Because 2.03 is close to 2, 0.98 is close to 1. Well, we can actually compute this. So we would say, well, plug in x equals 2, y equals 1. 2 times 2 cubed, that would be 2 times 8. And we have 2 times 1, which is 2, minus 1 cubed, so minus 1. So that's 16 plus 2 minus 1 is 17. So 17 is an approximation. But can we do better? And the answer is, of course we can. And we're going to do linear approximation. In other words, we're going to say, hey, I'm not just going to use information about the function at the point nearby, but also information about how the function is changing. Which is to say, I'm going to use information about the derivatives to help me say more along the lines of what we should expect it to happen. So, from here, we can say that we have this. We can say our function x of y is approximately f at ab plus f sub x at ab times x minus a plus f sub y at ab times y minus b. And this is for any ab. This is just sort of a generic statement. And the approximation is good whenever we're close. So that's why we want to pick 2, 1. We wouldn't want to pick 0, 0 because we're not close to 0, 0. So we can pick our point as being 2, 1. So it's approximately 2, 1 plus f sub x at 2, 1 times x minus 2 plus f sub y at 2, 1 times y minus 1. So that's what our function is behaving like. It's behaving like the tangent plane. Now we know a couple of these values to begin with. We know, for instance, that f of 2, 1, we just found that before, this is 17. But we need to find f sub x and f sub y. So let's come down here and do that. F sub x, well, first we'll find the generic term. That would be 6x squared plus y. And f sub y, well, that would be x minus 3y squared. So f sub x at 2, 1, that would be 6 times 4 plus 1, which is 25. And f sub y at 2, 1, well, that would be 2 minus 3 times 1 squared, which is 1, which is negative 1. So this will be 25, and this will be negative 1. So we can say that our function near the point 2, 1 is approximately 17 plus 25 times x minus 2 minus y minus 1. And so, again, let's just emphasize this approximation is really only good near 2, 1. If I'm away from 2, 1, the approximation is terrible. So, all right. How do we finish? Well, now we say we don't want to know f of xy, we want to know f of 2.03, 0.98, approximately. So we get that f 2.03, 0.98 is approximately 17 plus 25 times 2.03 minus 2 minus 0.98 minus 1. Well, that's 17. 2.03 minus 2 is 0.03. Times it by 25, you get 0.75. 0.098 minus 1 is negative 0.02, but then there's another negative. So I'm actually a positive 0.02, and therefore we get 17.77. And there we go. So 17.77, it's a better estimate because we're not only using what's the behavior of the function at 2,1, but how is the function changing at 2,1? Now you might say, wow, that's cool. Can we do even better? Maybe if we could get, say, the second derivative involved, could that improve it? The answer is yes, fantastic idea. And we're going to come back and visit that in a new session in the next week or so. Something to look forward to. Well, it's math class. Of course you always have something to look forward to. Everything is something to look forward to. All right, now let's try another one. Suppose that we're on this surface. X squared plus e to the xz plus yz is 2 plus cosine of xy. And we know that 0, 1, 2 is a point on the surface. Estimate the value of y, which satisfies the relationship when x equals 0.04 and z equals 1.97. Let's try to sort of grapple with what is this asking us, because it's not so clear. We know that this is a point on the surface. In fact, you might say, hey, there's something oddly familiar about that surface, like we've seen it before, because we've seen it before. It's one of the surfaces we did earlier today. It's this surface right here, x squared plus e to the xz plus yz equals 2 plus cosine of xy. And like we said, we checked that 0, 1, 2 is on the surface. So we know that there's this point 0, 1, 2 that's on the surface. So here we go. This is on the surface. Now, what we want to do is we want to say, well, hey, what if I move a little bit? 0.04 becomes the new x, and 1.97 becomes the new z. What is this value, the y value, so that I'm on the surface? Well, we can't answer that. So let's change it so that I'm maybe not on the surface, but I'm really close to the surface. So that's where the estimate comes in. So we don't actually have to find the exact value for y that makes it true, but we can say, where am I close? For which value am I close? So when I see the word estimate, I say, okay, what I can do is I'll do the following. I know that the surface near 0, 1, 2 is about the tangent plane. And what this means when we write this down means that the tangent plane mimics the surface very closely, so that if you were to zoom in very close, they are almost indistinguishable nearby. So what we'll do is we'll say, okay, let's see what's happening on the tangent plane. So we can use the tangent plane to produce our estimate. So which tangent plane should we use? So we talked about there were two variations, and here is where we should talk about the variation where we keep change. See, change can be very useful when you write in terms of x minus something, y minus something. So we're going to say 2 times x minus 0 plus 2 times y minus 1 plus z minus 2 equals 0. That's the plane format we'll use. Okay, so let's take this away. So what do we have? Well, we're going to plug in what we know. 0.04 for x, 1.97 for z. So 2 times 0.04 minus 0 is 0, plus 2 times y minus 1 plus 1.97 minus 2 should equal 0. Now 1.97 minus 2, that turns out that this is a negative 0.03. 2 times 0.04, that's 0.08. So what we have is 0.05, move it across. So 2 times y minus 1 is negative 0.05. And divided by 2, that says y minus 1 is negative 0.025. Now, pause for a second. Y minus 1, we should think of this as our change in y. So what this is saying right now is that the amount that y should change should be 0.025 negative if I were on the tangent plane. So if I'm on the surface, it's approximately negative 0.025. Now, since we wanted to solve for y, not to change in y, the last thing to do is to add 1 to both sides. So y is 1 plus negative 0.025, which, if you work that out, that would be 975.975. And there's the approximate value for what y will be, so that the value 0.04, 0.975, 1.97 is very, very close to satisfying that relationship. Okay. Well, let's look at one more. So an example. Your company is a leader in widget manufacturing. Oh, that's nice. It's always good to get a job with a company that's the best. Now, what are widgets? They're small cylinders. And they're supposed to have a radius of 2 inches and a height of 3 inches. Okay, so let's see what that means. So that says we have these cylinders, and okay, so here's my widget, and the radius should be 2 inches, and the height should be 3 inches. All right, there we go. But no widget machine is perfect, and there are always small defects. Now that's actually true for any machine. There's no perfect machine out there. It's like every meter stick. Every meter stick is wrong except one. Now, why is there one meter stick which is right? Because that meter stick is the definition of the meter, or at least it was. Nowadays, the definition of a meter is based on how far light travels in a vacuum in such and such time. But okay, so there's defects. So we're not always going to be 2 inches. We're going to be like 2 plus a little bit. We're not always going to be 3 inches in height. We're always going to be 3 plus minus a little bit. And so the question is, well, how much can we tolerate? So sometimes you're going to work with things and you say, look, I can have small defects, but they have to be very small. And so that's going to be okay. So let's keep going. The volume must be within pi cubic inches, and it is known that the height is within 0.1 inches of being correct. So the height, that says I'm within 0.1. So the question is, how much can we allow the radius to vary? In other words, what's the tolerance? How much can I let this radius move by? So let's think about what this is saying. And first off, why are we even talking about it at this point in time? So in some sense, the key word here is the word estimate. So saying, oh, okay. So estimation, so that's what we're talking about right now. So we're going to estimate, which means we're going to do something with a tangent plane. So we need to talk about volume. So how do we know we're talking about volume? Well, it says here the volume. So let's start with the volume of a cylinder. Volume is pi r squared h. So it's the area of the base, which is a circle, times the height. Now within pi cubic inches, well, that's saying that delta V can be plus or minus pi. So within pi, that's the delta V. So this is the within. So it's saying how much can volume change. So within plus or minus pi. So what we're going to do is we're going to say the following. We have that delta V is approximately partial V partial R delta R plus partial V partial H delta H. So this is the formula for linear estimation that we had a little while ago. So let's put in what we know. So delta v is approximately the derivative of v with respect to r, 2 pi rh. The derivative of v with respect to h, pi r squared, and delta h. Now, let's make a list. We know delta v is, well, plus or minus pi. We know pi is pi. R is supposed to be 2. H is supposed to be 3. Now, we also know the height is within 0.1 inches. So that says delta H is plus or minus 0.1. So, let's see what we get. So, we get pi. So I'm just going to look at the plus. So pi can be approximately 2 pi times 2 times 3 times delta r plus pi times 4 times delta h, which is 0.1. Now, the good news is all the pi's cancel. And then we get 1 is approximately 2 times 2 times 3. Well, that's 12 times change in r, and then plus 0.4. Move this across. 0.6 is approximately 12 delta r. Oh, we're running out of space downstairs, so we're going to come and finish it up in this little box here. Now, 6 isn't just any number. That's actually an easy number to work with. So 6, it's 6/10 or 3/5. So we get that delta r is going to be approximately 1/12 of 3/5. Well, if you divide, 3 goes into 12 4 times, that's approximately 3 goes into 12 4 times, yeah, so 1/20, or 0.05 inches. Which means that if our height can vary by as much as 1 inch, our radius is only allowed to vary by 1/20, 0.05 inches. So 1/10 of an inch versus 1/20 of an inch. And that's it. Now, is that exact? No, but it's a really reasonable estimate. Now you might have said, well, wait a second, what about the minus? Well, if you make everything minus, it all works out the same way. And you'll see that at the other extreme, it can be negative 0.05. So, all right, so now we have tolerances. This is actually an important thing to do, is to say, how much can we tolerate varying from what we expect, what the ideal should be. All right, well, good. That's it for today, and we'll keep talking next time.